Next topic, ordinary differential equation. First, let us see what is differential equation. An equation involving the independent variables and the dependent variables, both are optional, and at least one derivative term, which is called as a differential equation. Now let us see what is an ordinary differential equation. And a differential equation involving derivatives with respect to a single variable is called ordinary differential equation. This is an example for an ordinary differential equation: dy by dx plus y equal to e raised to minus x. Also d square y by dx square plus dy by dx minus 12y equal to 0, which is also an ordinary differential equation. Now let's see what is the order and degree of a differential equation. The order of a differential equation is the order of the highest order derivative present in that equation. Also, degree of the differential equation is the power of the highest order derivative in the equation. While seeing this problem, d square y by dx square plus n square x equal to 0. Here the highest derivative in the term is second order. Second order means second derivative is exists as the highest order. Hence the order of this differential equation is 2. And degree is the power of the highest order derivative exists in that equation. Here the highest order derivative is 1. The degree highest order of the derivative is 2, means the second order derivative is existing and its power is 1. So degree here it is 1. While seeing the next example, d square y by dx square the all cube plus 2y by dx equal to sin x. Here the highest derivative is 2. So the order will be 2 and its power is 3. Highest order, the power of the highest order derivative is 3. So the degree will be 3. Okay. So the order is taking as the order of the highest order derivative present in the equation, and the degree is the power of the highest order derivative in the given equation. Next, let's see what is linear differential equation. A differential equation is said to be linear if the power of derivatives and the dependent variables are either 0 or 1 and there are no terms involving product of derivatives and the independent variables, which means that the power of the derivative should be 1, which means if the derivative terms exist in while looking to this equation, dy by dx plus 3x equal to 0. Here the derivative power of the derivative is 1. So this is an example for a linear differential equation. Also here this equation contains second derivative term, first derivative term and the independent term. All of its powers are 1. So if the powers can be 1 or 0, 0 means the term cannot be existed. So the term will be contained, power will be raised to 0. Here the first derivative is existing, second derivative is missing. So we can written it as y double dash raised to 0. So the powers can be either 1 or 0. Then it will be a linear differential equation. The power of the derivatives should be 1 or 0. Also the dependent variable. Here y is the dependent variable and x is the independent variable. So power of y should be 1 or 0. Then next topic, homogeneous linear ODEs of second order. The standard form of a second order linear ODE is y double dash plus p of x into y plus q of x into y equal to r of x. This is standard form of a second order linear ordinary differential equation. And if the r of x equal to 0, then this equation is named as homogeneous second order linear differential equation. Okay. And if the r of x is is non-zero, if the r of x is non-zero, this equation is the non-homogeneous linear ordinary differential equation. Y double dash plus x into y dash plus y equal to 0, it is an example for homogeneous second order linear ordinary differential equation. And y double dash plus 25y equal to e raised to x into cos x, which is an example for the non-homogeneous linear ordinary differential equation. Since the r of x, value of the r of x is e raised to x into cos x, which is a non-zero value, so it will become a non-homogeneous linear ordinary. And if the value of the r of x is 0, it will become homogeneous linear ordinary differential equation. Then next topic, linear combination. What is a linear combination? We are taking two solutions y1 and y2 of these be two functions. Let y1 and y2 be two functions or two solutions of a differential equation. Then their linear combination will be denoted as like this. It means that we are taking the solution or two functions and multiplying it with two different or two arbitrary constants c1 and c2 and adding this term. The result value is named as the linear combination of y1 and y2. Next, fundamental theorem for the homogeneous linear ODE. It is also named as or also called as superposition principle or linearity principle. The principle says that for a homogeneous linear ODE, y double dash plus p of x into y dash plus q of x into y equal to 0. This is the standard form of a homogeneous linear ordinary differential equation. And if this linear equation consists of two solutions y1 and y2, then the linear combination will also be a solution of this differential equation. It is actually it is defined by this principle. Means the linear combination of two solutions of this equation will also be a solution. If it is expressing in simple words, let y1 and y2 be the two solutions of this differential equation, then their linear combination c1 y1 plus c2 y2 will also be solution for this differential equation. Next, let's see how we can solve a linear ordinary differential equation, a homogeneous second order linear ordinary differential equation with constant coefficients. Okay, so I'm considering the standard form of the second order homogeneous linear ordinary differential equation with constant coefficient. It is homogeneous, so the right side will be 0, and the p of x and the q of x is taken as constant since we are considering the equation with the constant coefficients. So here a and b are the constant terms. Now let us see what is the procedure for solving this differential equation. So I am rewriting this equation y double dash as d square y by dx square and y dash as dy by dx. Then considering the second order equation, d square by dx square as capital D square and d by dx as capital D. If it contain another term d cube by dx cube, we can replace it as d cube like this. Okay, so I am replacing this d square by dx square as capital D square and d by dx as d. So the equation can be written as d square y plus a into dy plus by equal to 0. And all these three terms contain y as common, so taking it outside, so we will get d square plus ad plus b of y equal to 0. And now I am replacing the capital D by lambda and equating it to 0, we'll get an equation. It is named as auxiliary equation. So the auxiliary equation will be lambda square plus a lambda plus b equal to 0. and it is a second order equation, so it contains two solutions. So let lambda 1 and lambda 2 be two solutions of this quadratic equation, and depending on the values of these two terms, lambda 1 and lambda 2, the general solution contains three format. So depending on the values of this, we can choose either of these cases as the solution format for the given differential equation. First case, if the lambda 1 and lambda 2 are real and distinct, means if the lambda 1 and lambda 2 values of the quadratic equation both are real numbers and different. For example, if the lambda 1 equal to 2 and lambda 2 equal to 3, both are real numbers and different. So the general solution format will be y equal to c1 e raised to lambda 1 x plus c2 e raised to lambda 2 x. Just replace the values of lambda 1 and lambda 2 here. Then we will get the general solution for the given differential equation. Now the next one, if the lambda 1 and lambda 2 are equal to lambda, which means both are real numbers and they are same. Which means if the lambda 1 and lambda 2 values are 2, both the quadratic equation, so solution of the quadratic equation both are 2, then will become real numbers and same. So the case will be the solution format will be y equal to c1 plus c2 x into e raised to lambda x. So just replace here the lambda value as 2, will get the general solution for the given differential equation. Next case, if the lambda 1 and lambda 2 are complex numbers. So I am taking the general format as if lambda 1 equal to some alpha plus I beta and lambda 2 equal to alpha minus I beta. Then the general solution format will be y equal to e raised to alpha x into c1 cos beta x plus c2 sin beta x. Since if the lambda 1 value equal to 1 plus I2 and lambda 2 is 1 minus I2, then the value of alpha here 1 and beta value is 2. Beta means the real number, imaginary part, and alpha is the real part of the complex number. Okay, then replace here alpha by 1 and beta by 2, we will get the general solution for the given differential equation. So depending on the values of lambda 1 and lambda 2 of the auxiliary equation, lambda square plus a lambda plus b equal to 0, we will get two solutions, lambda 1 and lambda 2. Depending on the format of this lambda 1 and lambda 2, either of these cases will arise as the general solution for the given differential equation. Now let us see a problem. Find the general solution for the ordinary differential equation y double dash minus y equal to 0. So here I am replacing, this can be also written as d square y by dx square minus dy by dx equal to 0. Next step, just replace this d square by dx square as capital D square and d by dx as capital D. So we get d square y minus dy minus y equal to 0. Now take this y as common outside, we will get d square minus 1 of y equal to 0. Now replace the capital D by lambda. We will get the auxiliary equation as lambda square minus 1 equal to 0. So the roots are plus or minus 1. It means lambda square equal to 1. Taking roots, we will get lambda equal to 1 and lambda 1 equal to 1 and lambda 2 equal to minus 1. Both are real roots and they are distinct. So the general solution format is c1 e raised to lambda 1 x plus c2 e raised to lambda 2 x. So replace lambda 1 by 1 and lambda 2 by minus 1. We will get this as the solution for the given differential equation. The solution is y equal to c1 e raised to x plus c2 e raised to minus x. It is the solution of the given differential equation y double dash minus y equal to 0. This is the procedure. Our next problem, solve the differential equation y double dash minus 5y dash plus 6y equal to 0. This equation can be written as d square y by dx square minus 5 dy by dx plus 6y equal to 0, and replace d square by dx square as capital D square and d by dx as capital D. So the given equation can be written as d square y minus 5 dy plus 6y equal to 0. Taking common y as outside, we will get d square minus 5d plus 6 of y equal to 0. Now replace this capital D by lambda. We will get the auxiliary equation as lambda square minus 5 lambda plus 6 equal to 0. While solving this quadratic equation, we will get two roots 2 and 3. These two roots are real numbers and at the same time they are different. So the case 1 is arise y equal to, so the general solution format will be y equal to c1 e raised to lambda 1 x plus c2 e raised to lambda 2 x. Take lambda 1 as 2 and lambda 2 as 3. Both are same if we take lambda 1 as 3 and lambda 2 as 2. So the general solution will be c1 e raised to 2x plus c2 e raised to 3x. And for finding the solution of the quadratic equation, we can use either the equation of quadratic equation format, or by factorizing we can find the roots like this. So here the roots are 2 and 3. This is the general solution for the given differential equation. Now next problem, y double dash plus y dash minus 2y equal to 0, and here we have some initial condition. This is an initial value problem, which means that there will be some initial conditions like this: y of 0 equal to 4 and y dash of 0 equal to minus 5, and these conditions are given because of we need to find the constant values in this equation solution format, which means we will have some constants like c1 and c2 in the final general solution format. So to using these conditions, these initial conditions, we have to find the values of c1 and c2, which means the general solution should not contain any arbitrary constants. There should be a constant value for the c1 and c2. We have to find it using these initial conditions. Okay, so first let's see what is the general solution format of this given differential equation. So I am replacing the y double dash as d square y and y dash as dy and minus 2y equal to 0. Same as above, just find the solutions. Continue the same procedure as like the previous problems, and I'm taking the y as common outside, d square plus d minus 2 of y equal to 0. Now replace the capital D by lambda. We will get the auxiliary equation as lambda square plus lambda minus 2 equal to 0. And using factorization method, I got two values 1 and minus 2. So these two roots are real and at the same time distinct roots. So the case 1 is arising here for the general solution format, c1 e raised to lambda 1 x plus c2 e raised to lambda 2 x. So here I am taking lambda 1 as 1 and lambda 2 as minus 2. So the general solution format will be c1 e raised to x plus c2 e raised to minus 2. So this is the general solution for the given differential equation. Next we need to find the values of this c1 and c2. For this we will use the conditions given in the equation along with the equation y of 0 equal to 4, which means the value of x equal to 0. When the value of x equal to 0, the value of y will be 4. So x equal to 0 and y equal to 4. So substitute y equal to 4 and x equal to 0 in this equation, in this general solution format. I am named it as equation number 1. So substitute y equal to 4 and x equal to 0 in equation 1. While solving this, we will get an equation c1 plus c2 equal to 4. Next, the initial condition is y dash of 0 equal to minus 5. Here, this condition means that the value of x equal to 0 when the y dash value will be minus 5. So, y dash equal to minus 5 and x equal to 0. So, the general solution format got it as y equal to c1 e raised to x plus c2 e raised to minus 2x. For applying this initial condition, we need first derivative of this solution. So just find the first derivative of this general solution. So the derivative of y is y dash, c1 x, derivative of e raised to x is e raised to x, plus c2 into derivative of e raised to minus 2x is minus 2 into e raised to minus 2x. So y dash will be y dash equal to c1 e raised to x minus 2 c2 e raised to minus 2x. Now we can apply this condition x equal to 0 and y dash equal to minus 5. The value of e raised to 0 is 1. So we get another equation c1 minus 2 c2 equal to minus 5. So while solving the two new equations c1 plus c2 equal to 4 and c1 minus 2 c2 equal to minus 5, we'll get the values of c1 and c2 like this. The value of c1 will be 1 and c2 will be 3. Now replace the values of c1 and c2 in this general solution format. The general solution is c1 e raised to x plus c2 e raised to minus 2x. So replace c1 as 1 and c2 as 3. So the general solution of the given differential equation is y equal to e raised to x plus 3 e raised to minus 2x. The next problem, solve the differential equation y double dash plus 6y dash plus 9y equal to 0. The procedure is same as above. Replace y double dash as d square and y dash as dy and taking the y as taking common outside and replacing the capital D by lambda. We will get the auxiliary equation as lambda square plus 6 lambda plus 9 equal to 0, which is the expansion of the equation lambda plus 3 equal the all square equal to 0. So the values of lambda will be minus 3 and minus 3. Okay, this can be also written as lambda plus 3 into lambda equal to 0. So lambda equal to minus 3 and lambda equal to minus 3. Here the two roots are real roots and they are same. So the case 2 is arising here. The general solution for the case 2 is c1 plus c2 x into e raised to lambda x. Here the lambda is minus 3. So the general solution will be c1 plus c2 x into e raised to minus 3x. Then next problem, y double dash plus 2y dash plus y equal to 0. The procedure are same as like above, like the above problems, replacing the y double dash as d square, y dash as d, dy and rest of all are same. Taking y as outside, we'll get the auxiliary equation by replacing capital D by lambda. The auxiliary equation is lambda square plus 2 lambda plus y equal to plus 5 equal to 0. Here we get actually the complex roots since the discriminant value will be negative. So while solving this quadratic equation, the roots will be minus 1 plus or minus I2. Okay, so the roots will be, I am taking lambda 1 as minus 1 plus I2 and lambda 2 as minus 1 minus I2. So these roots are complex roots, hence the case 3 is arising here. Lambda 1 equal to alpha plus I beta and lambda 2 equal to alpha minus I beta. Okay, so here the alpha value will be minus 1, means the real part of the complex number. So alpha is minus 1 and beta is 2. means the complex part of the imaginary part of the complex number. So the beta value is 2. So the general solution for e raised to alpha x into c1 cos beta x plus c2 sin beta x. So just replace the values of alpha and beta here. We will get it as c1 e raised to minus x plus c1 cos, replace b by beta by 2. So c1 cos 2x plus c2 sin 2x. This is the general solution for the given differential equation.